Okay guys, let's get started. Welcome to lecture 5. Today we are going to look at lower bounds on interactive proofs. And specifically we're going to study what happens when an interactive proof kind of uses a small amount of resources. Now of course there are various complexity resources we could talk about, but the main one we're going to discuss today is communication complexity. So we're going to try to study the question of, can interactive proofs with small communication complexity be used to prove hard languages? Okay. So let's start from maybe the most extreme case, right? You could define the complexity class IP PC equals 1. PC, I'm using it for prover communication, okay? Which means that these are languages decidable via interactive proofs where the prover sends a single bit, right? And you could ask, is this class trivial, for instance? Is it contained in P? Does anybody have an answer to this already? We have seen something that talks about this. So what interactive proof did we see in the first lecture?
For the graph isomorphism or non-isomorphism one, didn't that only send one bit?
Right, so the one for graph non-isomorphism, it said 1 bit. So, we've seen an interactive proof for a language, GNI, that at least at the moment, it is not known to be in P. So if that is your belief, then probably this rather restricted complexity class of interactive proofs where the prover sends 1 bit is not trivial. Doesn't mean it's powerful, but it's non-trivial. So this is telling us that even interactive proofs with small communication can decide non-trivial languages. But maybe we're not very interested in GNI because it's not complete for like an interesting class. In particular, it is not believed to be co-NP complete. So we could ask, potentially a more intriguing question, which is, could we hope for, say, an NP-complete problem like SAT, having an interactive proof where the prover sends a sublinear number of bits in the number of variables, right? Because remember, SAT has a trivial interactive proof. It's just you send me an NP proof. This is the assignment for that certifies that the formula is satisfiable. But maybe there's some other, smart way to prove satisfiability just with sending fewer than n bits. Okay? That would be like a nice thing to do. Right, so this is what I just said. So we know that SAT is an NP, so there's a trivial interactive proof. We're asking, is there one that, by using interaction, we gain somehow, somewhere, right? Maybe in communication. So to formally study this question, we're going to define parameterized complexity classes, for example, with prover communication, but we'll add a couple more parameters because it will help us understand it. So we're going to define the complexity class PC for prover communication, so PC bits. VC, that is the verifier sends VC bits, so this is the communication from the verifier to the prover. And VR, this is just the however many random bits the verifier is using during interaction. And right now we're just kind of discounting how many rounds there are. We just don't care. Obviously, if the prover is sending a small number of bits, there cannot be too many rounds anyhow. So we are implicitly taking that into account, right? And then we can also define AM with the same 3 parameters to be the very same thing, but with public coin interactive proofs. Okay, that could be a restriction. It turns out it's going to matter a little bit today. And as we vary these parameters, we want to try to study how powerful these complexity classes are going to be. Okay, so there's a variety of results that are known about interactive proofs with bounded resources. Here's one. So if we just, this is kind of like really the starting point. If we just limit all 3, we have some parameter that limits the prover communication, verifier communication, and verifier randomness. then whatever this language is, whatever any language in this class, we can show that we can decide it in time that is exponential in these parameters, times some polynomial factor. We'll see this theorem first. It is essentially just basically reproving the upper bound that we have already seen, just not as fine-grained. Because notice, if I just let all of these be poly n, we're just saying that we're inside in exp time, right? And in fact, we've shown in the first lecture that we can not only be in exp time, but in fact in poly space. But this is going to set the groundwork for a theorem that is maybe much less clear. So if we're going to put no restrictions on the verifier randomness, then we're still going to be able to decide the language in time that is exponential in the relevant, the communication complexity, in the two-way communication complexity. But we're going to have to use some randomness somewhere. We will see later why using randomness is important for this inclusion. Okay? Now, most of the lecture is going to be, in fact, the whole lecture is going to be dedicated towards Theorem 2. And once you prove Theorem 2, you kind of essentially get all of the main ingredients to prove two other theorems. I'm going to primarily state them and maybe just come back to them at the end of the lecture. One of them says, okay, so how about we drop any requirements on verifier communication and we only look at prover communication. But we're going to impose the restriction that it is a public coin protocol. Then again, we're going to be able to show that just because the prover is sending a small number of bits, I can decide the language in time that is exponential in that, okay? So we're going to still use randomness, okay? We get some extra log factor here, it's not very important. But what happens if we don't restrict this class to be about public coin interactive proofs? That is a final theorem that says that we get the same result, but we need some NP oracle here. And there's a good reason for why the NP oracle is here. We'll see that in a very moment. I just want to say that this whole exponential behavior here should make a little bit of sense, right? Let's just think of a much simpler setting of a proof system, that is NP proofs. Now, NP proofs where witnesses are small can't be languages that are too hard, right? Because if you don't feel like asking the prover for a witness, but you know that the witness is small, you can just iterate over all witnesses yourself, right? So that is kind of a similar behavior. We're going to be trying to iterate over possible interactions, but a little bit smarter, right? Because the interactions are going to be maybe bigger than what we can afford, right? This is the simplest situation where we can actually literally iterate over all interactions, but if we start relaxing some of the restrictions, then we're going to have to do something a little bit smarter than iterating over all interactions. But at a very high level, it is analogous to what happens if you consider an NP language where witnesses are small. It cannot be too hard of a language, okay? That is happening here as well. So at a very high level, there is a relation between communication complexity of an interactive proof and the time complexity of the language it decides. Now let's maybe compare some of these kind of statements with things that we know, so to at least make sure they're kind of consistent with them. So, for example, notice that the fact that graph non-isomorphism actually does have a 1-bit interactive proof, that is covered without contradiction by theorem 4, right? Remember, this one was a private coin interactive proof, okay? So it really has to fall inside here. And here, the prover was sending like a single bit, okay? And the verifier was actually sending not something small, it was sending graphs, right? So it was sending something pretty large. So it was nothing worth writing home about. Yet, notice that like if we didn't have this NP oracle here, we would get an inclusion that says that this language is in P, right? So we can't really afford, we don't believe that is true. So somehow this NP oracle saves us here, right? So there's actually slightly stronger results than these, but all I want to say is that you really cannot expect theorem 4 to hold without this NP oracle because of a statement like this one, okay? But wait a second, in the last lecture, we saw a public coin interactive proof for GNI. Will that contradict something about theorem 3? Well, turns out that when we did the transform, when we wrote the interactive proof for GNI with public coins, we ended up using actually a large amount of communication. If you remember, the prover was sending a pre-image that was a graph, so that there's n squared bits, and also an isomorphism to certify that H was in that magical set S. So overall, it is sending a linear, more than a linear number of, it is a linear in the input. The input is of size n squared. It is a linear number of bits, so that when you apply theorem 3, you get no contradiction. Like, it's okay, right? This public coin interactive proof was not one that we would consider had a small communication, okay? But we also learn that unless graph non-isomorphism is in P, we should not expect that GNI has a public coin interactive proof with a small number of bits, for example, a sublogarithmic. Okay, because otherwise you could apply this one and you would show that it is in like polynomial time. Okay? So all of these things, it's like good sanity checks, and it helps you interpret, some of the behaviors here. Now, in the prior slide, we also asked another question. Could we expect something non-trivial for SAT? Okay? Could we, for example, have an NP proof where for SAT, where the communication complexity is sublinear? Let's first consider what happens if we would find a public coin interactive proof with sublinear communication complexity. Well, we would get that SAT is decidable in 2 to the little o of n. Well, that is not good, right? It contradicts the exponential time hypothesis. So we definitely, for example, cannot expect, maybe SumCheck to give us something sublinear. SumCheck is a public coin style sort of interactive proof. So for SAT in general, we cannot expect such a thing. But what about private coin? Theorem 4 doesn't really rule out anything, and indeed it doesn't. But there is a sort of stronger variants of theorem 4 that didn't write in this lecture. I will kind of put them as references in the syllabus that basically tell you that even if you are fine with private coins, we really cannot expect general interactive proofs with sublinear communication for SAT. That is a bit of a bummer, but we will see in the next lecture that interactive proofs help us with other things, not in compressing witnesses, but in compressing, let's say, computation. So this is a collection of limitations. And today, as I said earlier, we're going to mostly look at theorem 1 and theorem 2. Theorem 1 is just going to be basically revisiting the upper bound just a little bit more carefully, and theorem 2 will be building on that to prove something a bit more non-trivial. Okay? Are there any questions so far?
Hi, Alessandro.
Yeah.
So when we talk about this communication complexity, so what soundness error and soundness and completeness error are we targeting?
The question was, in the context of today, what are the completeness and soundness errors? A third and a third. So we're picking the standard definition that is fairly kind of generous. It's okay. Sorry?
If we deplete it, if we want soundness, if we want to reduce the soundness error, then the communication complexity will go up, right?
Right, and so because we're proving, so the question was, if you want to reduce communication complexity, so reduce soundness error, then the communication complexity will go up. Yes, it will go up. And here we're proving lower bound, so we're fine with considering interactive proofs with constant soundness errors. And I won't be requiring any perfect completeness. So all of everything we're going to say will hold even if you have a constant completeness error. Yeah. Good question. Any other questions at this point? Because we're about to kind of jump into theorem 1. But yeah, I have to say, like, it's a bit annoying. Like, these results, I think, are mostly bad news. Like, the first kind of all of the lectures so far, they were basically saying, oh, look, interactive proofs are so strong. You know, GNI, CoinP, P-space. Oh, private coins doesn't even matter. Like, public coins can do everything, right? So it was like mostly good news, right? This is basically saying that, you know, for things that we might really do care about, like SAT, we can't expect any compression. But we will see in the next lecture that we can compress other things like computation of deterministic languages rather than witnesses for non-deterministic languages. Other probabilistic proofs later in this course, like PCPs, will not be subject to these limitations, that they can compress witnesses. All right, if there are no other questions, then I'm going to continue. So we have implicitly discussed the game tree of an interactive proof when we were discussing upper bounds. Now I want to discuss it slightly more carefully, just because we're going to be doing some manipulations all over it. So this should be, you know, fairly simple concepts. So a transcript of interaction is just a tuple prover message, verifier message, prover message, verifier message, so on and so forth, up to k rounds. K denotes the number of rounds. Today we'll be mostly working with what we could call augmented transcripts, which is the same thing, but at the end you append the randomness that was used by the verifier. Now, in a public coin protocol, the additional randomness is kind of redundant because all the randomness was sent throughout the interaction. But in a private coin protocol, just the fact that you have a transcript doesn't tell you necessarily all the information about what randomness the verifier used, so I have to tack it on. Okay? And now you give me some interactive proof verifier and some instance X, and that defines a game tree. Okay? It's just the tree of all possible augmented transcripts. So we can make a picture of it. It's going to have 2k plus 1 levels, 2k levels for, you know, each of the k moves of the prover and verifier respectively, and 1 level just for the kind of augmented part. So in the first level of the tree, the prover moves. So, you know, no transcript, and he chooses the first message. You know, there is a fan out here for all his possibilities. Then the verifier moves. This is the fan out of the verifier choices. Then the prover moves, and so on and so forth. And at some point, when everybody has moved, then there are the options of randomnesses that are consistent with the transcript so far. Okay? With the transcript that happened so far. So that is the game tree. So, you know, slightly more formally, the prover moves at even levels, the verifier moves at odd levels, and the edges from odd to even are prover moves, from even to odd are prover moves, and from odd to even are verifier moves, and the last kind of move is just the extra randomness. Okay, this should be, you know, we could have written this slide in lecture 1, right? We just didn't. We were being a little bit kind of sloppier, right? That is the game tree. Just like last time we were doing the upper bound, we are interested in understanding the value of the game tree, okay? And actually, specifically, we're going to be approximating the value. Well, let's first define the value. So the value of the game tree is just the value of the root, which is recursively computed, you know, depending upon where you are in the tree, starting to the bottom, ending up the top, right? So the value of a leaf node at some location here, right, is just either 0 or 1, depending upon whether the verifier, given that randomness and the prover messages, accepts or not. Okay, so for example here, if you're wondering the value of this node, you just take this path that leads you there, and you apply the verifier predicate to the instance X, all the prover messages, and the randomness. Okay? And then, you know, just obvious things happen, right? So if you are looking at a prover node, for example, this one, and you're wondering, I wonder what is its value. Well, the prover maximizes, so it's going to be the maximum of the children's values. That makes sense. And if you're looking at an internal node that corresponds to the verifier moving, then it's going to be just the weighted average of the children's values according to the probabilities for each of these edges. Alternatively, you can think about that the edges split down into many copies, and then you're just taking the actual average. So all of this makes sense, should be familiar. Just one small thing, notice that in the last layer, we have to add these randomnesses, and you can think about it as some fictitious final verifier message, and that's why we also get to put it there, right? Now, of course, you're not going to put here a randomness that is not consistent with the things up here, right? So you're going to only put here the randomnesses that are consistent with things that happened so far. Now, if x is an L, then I know that the value of the tree is at least 2/3. Why? There exists an honest prover that causes this certain choices in prover moves, like there's a choice here, that certifies that the value of the tree is at least 2/3. And if x is not an L, then because for every possible prover, the verifier accepts with probability at most 1/3, it means that when you take this maxima here, which is effectively considering all prover strategies, then the value of the tree is going to be at most 1/3. Again, we've already seen all this stuff. So to decide if x is an L or not, it suffices to approximate the value of the tree to within, let's say, an additive factor of 1/6 or 1/10 or whatever, right? So 2/3 and 1/3 are a third apart, right? So you slice it in 1/3 in half, you get a 1/6. So as long as your additive approximation is better than a 6, you're going to be fine. So now clearly, we have already seen with the upper bound that we can compute the value of t exactly in polyspace and exponential time. And today instead, we're specifically interested in relating, figuring out the time complexity to approximate the value of t when we have restrictions on resources such as prover communication, verifier communication, and verifier randomness. Okay?
Alessandro?
Yeah?
Can I ask a high-level question about why are we looking at these transcripts like this tree and going in this direction of approximating the value?
Yeah.
And relating?
So what is the high-level question?
Just why are we going in this direction? Why are we looking at things in this way? What are we trying to do?
Well, so we want to prove lower bounds. We want to say things like, give me a generic interactive proof where, for example, there's a small amount of communication. And we want to say that, oh, look, because there's a small amount of communication, I can exhibit a probabilistic algorithm that can decide a language, can decide that language in time that is related to the communication, right? Now, it is a generic interactive proof. I don't know anything about it. So, the only structure that we have is the game tree, right? It's, that is the thing that is given to me when you give me an interactive proof. And intuitively, if you restrict communication, this tree is going to become smaller and smaller, right? So and this tree defines the value, right? So, and the value is the key to deciding the language, right? So we want to kind of understand this tree or approximate things about this tree so that we can approximate the value of the tree, which tells us yes or no for the given instance in time that, is related to the, communication complexity. Hopefully that answers the question. Again, intuitively, if you give me a generic interactive proof, I got nothing but the tree. That is the thing that it is, right? All right, good question. More questions? Okay, cool. So now let's look at the first theorem. It's kind of the easy one. Now we're going to, should be a V here. We're going to consider giving a generic interactive proof where you have a parameterized bound on prover communication, verifier communication, and verifier randomness. And I want to tell you, because that is the case, I can decide the language in time that is exponential in all of these quantities. All right? All right, so let's, just for notational convenience, set C to be a bound on communication complexity and randomness. Okay? Look, this is the upper bound that we already proved in lecture 1. The number of nodes in the tree is at most 2 to the big O of C, where C is this quantity. Why? Well, there's at most 2 to the C possible transcripts. And each has at most 2 to the C possible augmentations. So we have at most 2 to the C, 2 to the 2 times C leaves. Okay? And I'm being even sloppy here because, I could even just write 2 to the PC plus VC plus VR. Okay? So, we have time for that. We can just compute the value exactly in 2 to the O of C time by just writing out the tree and following the recursive computation of the value of the tree. We're not approximating anything, we're just computing it on the nose because we have, in fact, here we don't even care about space, so I can actually write down the tree. In our upper bound at the beginning of the course, we were trying to say we can traverse the tree. Here I'm saying, yeah, just write it down, not even a problem, okay? We have the time for that. In fact, here I could even be even more careful and say that the verifier communication doesn't even matter that much because there cannot be more verifier communication and there are possible prover communication and verifier randomness. These are the only degrees of freedom, like in the transcript. So I can even ignore the verifier communication. Now, just some small thing that maybe is going to help visualize what we're going to do to the tree later. How do we compute the probabilities of the verifier messages along the way? One way you can think about it is that in each internal node where the verifier moves, the set of all, you can just keep the set of all random strings consistent with the transcripts so far. And then when you want to generate the probabilities, you just iterate over this set, kind of the possible randomnesses, and they will partition the set according to the verifier's move, right? So once you have partitioned these randomnesses by the next verifier move, then you have the weights. Also notice another thing that may not be obvious is that we're not partitioning when the prover moves, right? When the prover moves, that's his move. In particular, it could be that the same randomness may appear in more than one leaf, right? Because when the prover moves, you're going into different subtrees, but it shouldn't affect kind of which randomnesses are consistent so far, right? It's only the verifier messages that affect that, right? So far.
Okay. Alessandro, this prover communication and verifier communication, how does it relate to that transcript, A1, B1, A2, B2? Is it the size of the AIs plus the length of the transcript, or what is it exactly?
Yeah, so PC is the sum of the AIs, and VC is the sum of the BIs.
So I see the sum of the sizes of AIs and the sum of the
BIs. Yeah. It is
not just, I see. Because in principle, it seems like I was initially thinking they should be the same, because for every prover message, the verifier sends another message back, but I guess you're looking at the actual sizes of the messages. So I'm not counting rounds. I'm looking at literally how many bits are being sent in each direction across the entire interaction. Okay, I am ignoring how many rounds there are implicitly, right? Because anyways, if I'm bounding the amount of bits, there cannot be too many rounds, right? If I'm saying the prover sends at most 10 bits over the entire interaction, there cannot be 100 rounds. There's at most 10 rounds, right? Mm-hmm. But the tree, the depth of the tree is related to the number of rounds, and PC and VC don't really change the tree, right?
They change the fan outs, right? And they also change how deep the tree is because
change the fan outs.
It's basically the they change the fan outs, right? So if you kind of multiply all the possibilities across all the prover moves, it's gonna be a quantity that is at most 2 to the PC, right? You cannot have the product of all the prover fan outs to be at more than 2 to the PC. Similarly, there cannot be a product of all the verifier fan outs that is more than 2 to the VC. Okay? All right, good questions. Okay, anyways, so kind of theorem 1 is just basically reloading state about how to, sort of actually compute the value of t. But now we want to go beyond this, and we want to start relaxing some of these requirements, okay? And things are going to get a little bit complicated as soon as we drop one requirement, and that is we want to look at the situation where we just bound communication complexity in both directions, but we allow the verifier to use potentially a large amount of randomness. Large, I mean some arbitrary polynomial, right? It could be that VC is, I don't know, n to the 3, right? And star is, I don't know, n to the 100, right? Or maybe VC is like square root of n, and this is n. So we're just ignoring how much randomness the verifier uses, but we want to bound just the actual communication. Notice that here, we immediately see that our algorithm to decide the language is going to be a probabilistic algorithm. It's going to decide the language with bounded error, two-sided bounded error. And we have, again, this exponential dependence, and we don't have the star because the star is kind of, doesn't belong. And we just have 2 to the PC plus VC, which is just the total communication. All right? So, all right. So again, for notational convenience, let's call C now be a bound on communication only. In this case, it is the case that there are still at most 2 to the C possible transcripts, and there are, because of that, 2 to the order of C internal nodes in the tree. But now each transcript may have 2 to the poly n augmentations, right? Because the randomness, could be an arbitrary polynomial, and when you get to the bottom of the tree, there is like a huge fan out, okay? So actually, now we are at a point where we cannot construct the game tree in the allotted time explicitly. Our allotted time is 2 to the O of C, but we do not have 2 to the poly n. Okay, poly is just some arbitrary polynomial, whereas C is a specific quantity, which you think of as small. And in fact, we cannot even compute the probability of verifier messages inside the tree, because remember, like to take the weighted average within a node inside the tree, the way I was doing that, I was iterating over all randomness, and I was seeing which randomnesses correspond to which verifier messages. But now I can't do that anymore. There's just too much randomness to go over. I do not have the time for that. Okay, so even though there's a small number of the verifier sends a small amount of bits to the prover, figuring out with what probability it does so, I cannot actually do that. Okay, it's just too much randomness to so this seems like pretty annoying. Okay, but we haven't used the fact so far that it suffices to approximate the value. Okay. And so this is where randomness is going to come in to help us. We'll use randomness to approximate the value of t rather than computing it. And by virtue of the fact that we're only approximating it, we'll be able to get by indeed with 2 to the O of C time. Okay? And actually the algorithm that does that for us is very simple. It's just 2 lines. And then there's just a question of, why does it work? So here's the probabilistic algorithm. It has really 2 lines. Line number 1 is it's basically the only thing we could ever do. We're just going to say, look, there's too much randomness. Fine. I'll just sample some representative randomness. Just sample randomness 1, randomness 2, randomness 3. At some point, I just run out of time because that's my time. And I'll just stop. And I call this representative randomness big R. Okay? And I'll just make do with it. I'll just basically construct a so-called residual game tree. Okay, and I'm just imagining as if the verifier is only using these randomnesses. Okay, it's like a sparse subset of the much bigger set of randomnesses, and I generated this sparse subset uniformly and independently at random. And so now I exactly compute the value of this residual game tree. And again, the residual game tree is defined the same way, except that just the set of the base set of randomness against which the tree is defined is just this R that I sampled right now. And first, let's just see that this algorithm, as described, really does meet our budget of time, because the residual game tree, by definition, has size that is 2 to the order of c times the amount of possible randomnesses, but here I sampled 2 to the c times c randomness, so the entire thing is 2 to the order of c. And so the only question is, why does this algorithm work? It clearly is probabilistic, and it clearly runs in the amount of time. We just need to show that, why does it work? Okay?
What is VR? You said 0, 1 VR, but VR is not defined.
Well, VR is just whatever the randomness complexity is. I'm not bounding it, but it's still something, right? So here's a star. I didn't want to put a star here, I put VR, right? But we're not counting it, it's just whatever it is. Good question.
Excuse me.
Yeah.
How do you decide on the length of each random screen, like the RIs when you sample them? If you don't know VR, then how would you decide how long each string should be?
The question is, how do I know how long it is? Well, I know VR is just that it's not small, right? When you give me a verifier, right, it runs in some concrete polynomial time, right? And we often use the fact that it is a polynomial time machine by talking about its time, for instance. So I could bound this one by the running time of the verifier, for example, right? Now we're not like doing this in a real world product where I literally need to know that. I mean, it exists, right? It is a fixed polynomial time, and so whatever it is, just put it there, right? I'm constructing an algorithm to show that a certain language, is in this complexity class, right? That's all I need to know, is that this algorithm exists, right? Good question.
So in other words, you could put the VR instead of that star in your theorem statement, and then VR would be defined, because you're proving it for.
Sure, yes, and I could put VR here, and I could put the union here across all VRs that are in poly n, right? And this entire union would be in there. And in fact, this is what star means, right? So I'm considering that whatever VR is, it was going to be in a complexity class that doesn't care about VR, right? But I can also put many other things here, right? I can put the time complexity of the verifier, the space complexity of the verifier, we often refer to well-defined quantities. In fact, the time complexity of the verifier, which is definitely there, right? It's the verifier of an interactive proof runs in a specific polynomial time, right? It is a polynomial time machine, so there must be some polynomial that bounds its time. Whatever that time is, you can use it to bound a bunch of things: the space, the verifier the randomness complexity, right? So we're not really using fine-grained information about randomness. It's just something very coarse. But good questions. So hopefully the algorithm itself is clear. We are just basically running the previous algorithm, but we have sparsified the set of possible randomness. And we want to argue that when we do that, we get a value that approximates the correct value. Okay, and that is what we're going to show. There's a question about where does the poly n statement over here come from? For example, at the bottom of the tree, we need to evaluate the verifier predicate. And we do it at every leaf of the tree. So we're doing 2 to the O of C work, but there's a multiplicative overhead that we pay in terms of evaluating the verifier predicate. So we kind of absorb it here. You might ask, wait a second, but why don't I just put it in the exponent and 2 to the plus log n? I could do that, but notice that I cannot make it literally go away, because maybe PC and VC are sublogarithmic, right? And so I can't just assume that if I put in the exponent, it will be absorbed by PC and VC. Maybe those are sublogarithmic. So I have to keep track of it somewhere. And in this case, I find it convenient to keep it outside of the exponential. Okay, good question. Okay, so now we've described the algorithm, and we're only going to focus on arguing why the algorithm is correct. Okay? And specifically, the lemma we're going to prove that exactly captures its correctness is this one. We're going to prove that over a random choice of kind of sparsified randomness, the exact value of the residual tree and the exact value of the original tree are not far from each other with high probability. Okay? And that's exactly what we want, right? We wanted to decide the language with bounded error, right? So this is telling us that with high probability over the randomness of the algorithm, the answer will be correct because we'll be returning a value that is pretty close to the correct value. So if this one was, I don't know, 2/3, at least 2/3, then we'll get a value that is at least 2/3 minus a tenth, right? Which is definitely far away from a third, so we are comfortable saying, yes, it's in the language. And if instead here we get a value that is at most a third, then in the worst case, when we compute this value, we might get a third plus a tenth. But a third plus a tenth is definitely far away from 2/3, so we're comfortable saying, no, it's not in the language. Okay, so this is exactly capturing the correctness of the algorithm. There's a question that says, is the choice of 99 over 100 significant, or is it the lowest that it could be? No, it's not very important. I mean, it cannot be, for example, I mean, this is basically going to be related to the soundness error of the algorithm, right? So it's not that important. So whatever is your error here, if it is, for example, some arbitrary constant, then it is telling you that the probabilistic algorithm that you obtain to decide the language has that soundness error, right? So in this case, the soundness error will be 1 over 100. Sorry, no, I shouldn't call it soundness error. It's a two-sided error, right? So it's both completeness and soundness. And it's not even like proof system, it's like BPP, right? So it's a two-sided error of probabilistic algorithm. So this is telling us that the two-sided error is going to be 1 over 100. And if you reduce this one, the soundness error is going to increase, right? But just like in interactive proofs, once you have a constant two-sided error, you can amplify it using repetition and majority. Whenever you see arbitrary constants like this, they're typically quite arbitrary. And we'll see where they come from, and you can sort of parameterize the entire statement if you want. Not that difficult. All right, so this is the correctness of the algorithm, and now we're going to try to prove it, okay? So basically, I mean, it's actually not that sophisticated, but since it's the first time we do a concentration argument in this class, we're going to sort of do it slightly more carefully, also because it's translating it to a concentration argument requires a little bit of care. So basically, the proof is just a concentration argument applied to the right random variables. So let's define a modified verifier, let's say V superscript capital R, to be the original verifier, but now it just samples its own randomness within R rather than the whole space. Okay? And observe that the value of the residual tree is just the maximum acceptance probability of this modified verifier when interacting with any prover strategy, right? It is actually just the game tree of just some funky verifier that draws randomnesses in a very weird way. Okay? And so now we can talk about interactions of provers with this verifier. We're going to define this kind of delta quantity. It depends on a particular prover and a choice of randomness. And it's going to be the difference between two convincing probabilities. We're going to take the prover, and on the one hand, we're going to pit it against the original verifier that draws its randomness from the whole space. On the other hand, we're going to say, let's see how the prover performs against a verifier whose randomness is drawn from the sparsified space. And using this notation, I can exactly, this is the definition, right? I mean, from this definition, this follows, right? this verifier exactly takes its randomness in this way, and this verifier exactly takes its randomness in this way, right? So this delta here is precisely the difference between these two probabilities. Now, notice that only the first term depends on R, and the second one just depends, both of them depend on P tilde, of course, but only the first one depends on R. What we're going to do is that we're going to prove, so we have fixed a particular prover, right? We will deal with all provers later on. For now, we are fixing a prover. Intuitively, later on, we're just going to take a union bound over all provers. But we have fixed a prover, and we want to prove that with high probability, this difference is small over the choice of randomness. Okay? Once again, it's a fairly intuitive statement. We're saying the verifier is taking a large number, but not an enormous number, of randomnesses from the whole space. And we're saying that with high probability, whatever this verifier is doing in this game and the original verifier is doing here, these two probabilities are going to be the same for the same prover. Okay, when the same prover is playing against this verifier or this verifier. Okay? So, in this slide, we're just going to prove exactly that claim. That's exactly what I wrote earlier. Given any prover, the probability that this difference is small is large. In other words, the probability that this difference is not small is very small. Okay? And here we're gonna, this is where the concentration argument is applied, and this is where we need to define the suitable random variables. So we're going to define Zi to be the random variable that you get when you look at the decision bit of V on the ith random string in R. Right now, Ri was a uniform independent randomness in the whole space. I am specifically saying that take the ith one in our sampling procedure and call Zi whatever the verifier says on that one. Okay? Now the random variables Z1 through Zm are independent and identically distributed because R1 through Rm. Remember that the set R was produced with sampling with repetition, right? It was saying sample R1 at random from 0, 1 to the VR, sample R2 also at random from 0, 1 to the VR. This process generates M identically distributed and independent random variables. On each of those, I define a variable Zi. These also are IID. Okay? All right, that's great. We have independent random variables that are identically distributed. Notice that the expectation of any one of these is just the probability that the prover convinces the original verifier. Because, again, each of these was random within the whole space, which is exactly what the verifier would have done, right? Moreover, let's look at this carefully. I claim that this random variable, or rather this quantity, okay, equals this probability. Okay? Let's think about it. R is a random variable, right? So this probability is also a random variable, right? Now, what is this probability over? This is the probability over the choice of randomness within R, right? But the choice of R, is a random variable, so that is a random variable, okay? And I claim that both of these are, these two are the same random variable. Let's try to think about it. Fix a particular choice of capital R. This probability says pick a random Ri in R and just see what the verifier does on that one. Okay, but either he does this or that or that or that, and any of them is picked with 1 over m probability. So this must be the same, right? All right. So now we just conclude the proof via Chernoff bound. So this is the statement that we want to study. Here it is. I've just copied it down here. Here I'm just expanding it, right? Using the definition from the prior slide. What was this difference? It was the difference of the probability of P tilde playing against the verifier choosing its randomness from R, and P tilde playing against the original verifier. And we're looking at the absolute value of this difference and asking, is it greater than a tenth? And now we can actually translate each of these. Why? Because look, this probability is exactly this quantity. And remember here, we have two levels of probability. There is a choice of R and a choice of randomness within R. Okay? So this probability here is itself a random variable, and we're replacing them by these random variables. Okay? This over here is just a constant, right? Because it is independent of R. Okay? And here it's saying what happens if you pick a random string from within all possible ones, but that's just the expectation of any one of these. For example, the expectation of the first one. Okay? And then we just apply some, Chernoff bounds. There's like a million Chernoff bounds out there. This is the particular one that I applied. It says, give me x1 through xm, they are IID in the 0, 1. Then the probability that the empirical average deviates from the mean is greater than epsilon is 2 times epsilon minus 2 epsilon squared times m, where m is the number of these. And I'm just like, pattern, and here you're just pattern matching, this is the empirical average, this is the expectation of any one of them, epsilon is 1/10, this is the epsilon squared, we had m of them, so, using the same notation here, and that's exactly what we get up here. So the proof of this claim is just apply a Chernoff bound. You just need to figure out what variables you're applying it to. Okay? Are there questions here? Just the only tricky part here is there are two levels of probability, right? We're looking at the probability over choice of R about statements of probabilities, okay? So these are random variables relative to R, but once you fix R, Ri is a particular string, so Zi is either 0 or 1, right? So I even dedicated an entire slide, so the entire proof kind of has space to breathe and it's not cramped. Hopefully it kind of makes sense. Are there questions about this proof?
Hi, Alessandro.
Yeah.
I got confused a bit. So the line there where you have written the summation of all Zi's by m, so that is a random variable. But the right-hand side seems like a probability value.
It's also a random variable. So the question is, this is a random variable, but this is also a random variable relative to R, right? Like for different choices of R, you're going to get different probabilities because the verifier is going to sample a random Ri from within different R's, big R's, right? So again, fix R, for a fixed R, this is a number, this is also a number, right? Because if I fixed R, this is just Zi is either 0 or 1, right? Because having fixed R, if I look at the ith element in R, it's just a particular string. On this string, the verifier either says 0 or 1, okay? So for a fixed R, maybe I should have written maybe at the beginning here, say for any R, right? The following holds. This fraction equals this fraction, okay?
I see. So the output of the probability is output of the random variable is a probability value on the right hand.
Yeah, exactly. So this is the random variable is a random probability, okay?
Right. Okay.
Yeah, over the choice of R. But if you fix R, then that is a fixed probability, and this is also a fixed fraction, which equals that probability, okay?
Got it.
All right, more questions about this slide? Okay. All right, so this was just like to prove this statement here. Now we kind of pop the stack, right? We come back. We proved it. And now we're going to conclude the proof, okay? So now here we're looking at specific P tilde, okay? But notice that so far we haven't used yet our hypothesis, that the interactive proof has small communication. Like somewhere you need to use it, right? Because we're going to get like a conclusion that is non-trivial. So we need like something to help us. Now is where we're going to use it, right? We're going to say, look, a prover is just a function from the transcript so far to the next message. Okay? So there cannot be too many provers, right? So there's at most 2 to the c, 2 to the c, also known as 2 to the, open parentheses, c times 2 to the c, close parentheses, because the input and output sizes, they're both bounded by 2 to the c. So here, exactly here, I'm using the fact that the prover communication and the verifier communication are both bounded by c. Input sizes are at most c, sorry. I had the too many exponentials, right? So here I have used both directions of communication are small, right? Because the input includes also verifier messages and the output are the prover messages. So because both of them are small, there cannot be too many functions that describe the prover. So that means that I can take a union bound on all such provers, and I just need to make sure that my kind of probability up here is large enough. How do I make sure it's large enough? Well, I just control it by taking enough, I make my sparsification with enough randomnesses. And specifically, I'm going to take this many. Okay, a little bit more than the provers. Or at least, like, there's so many provers, I'll take it, I don't know, 100 times that. So now the probability over a choice of R that exists some prover that makes this difference greater than 1/10 is at most, by union bound, the probability that the sum of the probabilities across specific provers. But for a particular prover, I had this upper bound. So here we are, right? So it's 2 times c to the 2 to the c, that's the number of provers. And this is the expression that we got for a particular prover. But look, if I make m, I don't know, like 1,000,000 times 2 to the c times c, then this is going to be less than 100, 1 over 100. And I can do that, right? Because I was fine with sampling this many randomnesses, okay? And then, but wait a second, okay, so this probability is small, but I was interested in this one. I was interested in the probability that the exact value of the residual game tree and the exact value of the original game tree are not too far away. I mean, if the probability that they are far away is small. But I talked about something else. Well, now we're going to argue that this probability is only bigger, okay? And so that then we're done. So let me just convince you of this last inequality. Actually, before I do that, let me just stop again for questions. All I've done is that for a particular prover function, the sparsification, the probability that the sparsification for that prover is bad is very, very small, okay? Right, so we're saying fix a particular prover, okay? That is, basically considering a particular choices in the prover tree, all right? And we've sparsified the tree, and we're saying the probability that the two probabilities are far away from each other is extremely small. And in fact, we can make this as small as we want by making m larger and larger. But fortunately, there are not too many provers because communication is bounded. So we can afford to just say, well, whatever, like, there's not too many provers, each prover must be doing something. And so overall, the probability that there is some prover that makes the sparsification bad is pretty small. All right, but now we need to talk about how to relate the values of the tree and the fact that there is a prover that makes sparsification bad. They seem to be basically the same thing, but let's just check that they are indeed related. So let me do that. So fix any choice of R, okay? And I want to argue that if this is the case, then this is the case. That will be enough to kind of show this inequality. The event on the left implies the event on the right. So, okay, so we have an absolute value here, so we need to consider both sides. Suppose first that the for a particular choice of R, the value of the residual game tree is greater than the value of the original game tree plus 1/10. Well, so what does that mean? So let's think about it. Remember that the value of the tree being high, it means that there is some prover that achieves it, okay? So let PR star be the best prover inside here, and P star be the best prover inside here. These may be different provers for all I know, right? But whatever they are, the probability that this one wins is greater than the probability that this one wins plus 1/10, because that's exactly what we wrote here, okay? Notice that here, I'm using a fact that I mentioned earlier, that the value of the residual game tree, it's like making a prover play against this funky verifier. We're using this fact here, all right? Okay, but what we are actually interested in was finding a prover, the same prover that plays in both games. Okay, but it's easily done, because if this is the best prover, picking the other prover cannot be better, right? Because this was the best prover. So if I pick the other prover, then it cannot be better. And now this prover is the one that separates the two probabilities. He's the same one that plays against the funky verifier and the original verifier. And this prover separates the two probabilities with greater than 1/10. And the other case is symmetric. If instead the exact value of the original game tree and the exact value of the residual game tree is greater than if the exact value of the original game tree is greater than the value of the residual game tree plus 1/10, then that tells us that there is some best prover in the playing the normal verifier that is greater than the best prover against the funky verifier plus 1/10. But again, this funky verifier cannot be worse. It's the best one than the verifier. This prover cannot be worse than the verifier that was playing over here. So now we're saying that this prover is the one that separates the two probabilities. Okay? So this is telling us that regardless of the two sides, whichever of the two conditions holds about the absolute value, we can infer that there is a prover that makes these two probabilities apart, like farther away from each other than 1/10. Okay? And we already bounded this probability. That was this computation. So we know that overall, the probability of a random choice of R, that the exact value of the residual game tree is far from what we want, is small. This proves that the algorithm that we wrote earlier is correct. Questions? So I tried hard to section the material across slides to have some permanence, but without a lot of resolution, I cannot make miracles. But let me just kind of take a step back here. Starting from here, all right. Again, what we wanted to show was this inequality, okay? And what we've done is just a concentration argument that always holds, by the way, doesn't use any hypothesis, followed by a union bound on a number of provers, okay? And the way we studied it is we said, well, this guy is just very related to this quantity as we proved towards the end of the proof. And this quantity singles out specific provers. That's why for a particular prover, we can talk about the concentration. And then we took a union bound over those provers, right? And how do I go back? Further back. All right. And this R that the probability we were taking throughout the proof was the choice of this one was to defeat all provers, okay? Because we have roughly this many provers, we're gonna make, and this one appears in the exponent thanks to the concentration bound, then, by making this specification large enough with this M that we can afford, we were able to defeat all provers. so that when we compute the exact value of the residual game tree here, we're going to be fine. Okay? And this was just theorem 2, okay? Where we said we're not going to pay attention to how much randomness the verifier is using. Are there questions? Now, the other 2 theorems are a little bit more involved. Not that much, but let me speak at high level kind of what you do for each one of them. I was debating whether to make slides for them, but then I don't know. I got tired myself after writing the proof for theorem 2. I thought maybe I'll just speak at high level with, let me just go back here and go back to the 4 theorems, right? So we have seen this theorem and this theorem. This is how we spent, most of the lecture, okay? You may wonder, all right, so what are we going to do if we also remove the requirement that a verifier sends a small number of bits? Well, first you should realize that the previous proof fails as is, because it is not the case anymore. There's a small number of provers. We cannot afford a union bound over them anymore. Okay, so what are we going to do? Well, the idea is that we're also going to not consider all possibilities inside the tree. I mean, what else are we going to do? We're going to sample representative verifier messages, okay, and not consider all possibilities. So we are going to choose, we're going to say, okay, I don't know, we have some budget of how many verifier messages we may want to consider. This budget is going to be something related to the parameter C, and we're just going to consider like some number of them. This is going to further sparsify the tree even more. In fact, it's like the now provers are not even going to see some of the messages that were present in original interaction. And intuitively, the analysis is going to be kind of building upon the analysis of theorem 2. And the way it works is through a so-called hybrid argument. Basically, we're going to consider, so these are like, proof techniques coming, for example, from cryptography, where you consider intermediate notions from the tree that we consider in theorem 2 to the tree that we consider in theorem 3. So we're going to say, okay, well, in theorem 2, we didn't sparsify any of the verifier messages internally beyond whatever is implied by the randomness, but we didn't artificially do that. Whereas here, we're doing it at every level. So consider intermediate trees that say, okay, well, do it at the first level, at the first and the second level, at the first and the first, second, third level, and you consider like number of level intermediate options, and you're going to prove that you can make the approximation between any 2 levels like pretty good, okay? Good enough so that, when you pay for the cost, the approximation between the first and the second and the third hybrid, third and the fourth hybrid, all until the hybrids, you're going to have an overall a good approximation. But you need to make sure that the approximation between the hybrids is something like 1/6 times 1 over the number of hybrids. And 1 over the number of hybrids is something related to the round complexity, which is just some polynomial. So you can consider polynomially many hybrids. So that is essentially how it works, is just building on that and basically applying this approximation argument between layers of 2 trees that differ everywhere but for 1 layer. Now, in order to be able to sample these random verifier continuations, if you kind of think about it, you're going to use the fact that the protocol is public coin. Conversely, it's not at all clear how to make random continuations if the protocol is private coin. It's just not clear at all. Okay? So the oracle here is basically helping us implement this subroutine. So you can think of the theorem 3 here to be written with access to a subroutine for random continuations from the transcript so far. And theorem 4 is just basically theorem 3 by showing that you can implement for a private coin protocol a random continuation subroutine. Okay? So kind of to summarize, theorem 1 is pretty easy, theorem 2 is pretty involved. So it's a pretty big jump from theorem 1 to theorem 2. From theorem 2 to theorem 3 is just basically a hybrid argument and rearranging the argument, so it's a medium jump. And from theorem 3 to theorem 4 is actually a pretty small jump. You're just kind of isolating this random continuation and just arguing that with an NP oracle you can implement it efficiently. I didn't write a theorem 5, that there's a strengthening of this one that in follow-up work I will add a link to that paper in the syllabus.